Good morning, everyone. Today, my topic is about the design of broadband input output circuits. I am G. Naresh from ECE section. This is the PPT of analog and pulse circuits subject. Let's get into the topic. The transport of high speed data to and from chips requires input and output interfaces with the commensurately wide bandwidth. In addition to the parasitic capacitance that the output divider in the transmitter and the input stage in the receiver present to signal path, both interfaces must also deal with the capacitance associated with the electrostatic discharge, that is ESD protected devices. The input output design thus becomes increasingly more challenging as great, greater speed are sought. In this article, we design input-output circuit for a data rate of 40 GB per second with a single-ended voltage swing of 0.5 V peak-to-peak voltage, that is V peak-to-peak voltage VPP, while focusing on the use of T-coils. General consideration: the output pin, a generic broadband transmitter, incurs three capacitors arising from the divider circuit, the ESD device, and the pad shown in the figure A. This is the figure A is an example. The figure A is an example with the respective values. CDR is equals to 100 F farads and CE is equals to 3F farads, 300 F farads, and CP is equals to 70 F farads. The network drives a transmission line having characteristic impedance of RL is equals to 58 and employs a back transmission resistor RT is equals to 50 ohms. So has the absorbed signal component that are reflected from the far end of the line, suppressing secondary reflections. RT does increase the power consumption by a factor of 2, but it proves necessary for data rate above the few gigabits per second. So this is the figure 1 and it is the driver where CDR, the CDR is equals to 100 F farads and CE is equals to 300 F farads and CP is equals to 30 F farads. And this figure 1 shows a generic transmitter output stage, and figure 1b shows its output I diagram, and C shows the output return loss. So to transmit the broadband data, the output structure of figure 1 must provide a bandwidth approximately equals to 70% of the data rate, 28 GHz in our case. So has to introduce negligible intersymbol interference ISI. Moreover, the circuit must exhibit acceptable output impedance matching to suppress secondary reflections. Unfortunately, the parasitic capacitance in the figure A prohibits the circuit from meeting either of the two criteria. The minus 3 dB bandwidth is limited to 1 by 2 pi RT parallel to RL into C to T, that is equals to 13.5 GHz, and CTOT is, that is C total, is equals to 470 F farads. Also S22 is equals to Z22 minus RL by Z22 plus RL, where Z is the impedance, and that equals to RT into C total into omega by under root 4 plus R square T C square total omega square. And figure 1 and figure 1b and C plots the output I diagram and H22 respectively. In our simulations, we assume that the 40 GB per second data has 10 picoseconds rise in the fall times. The eye in the figure B has a vertical opening of about 64% of the nominal swing, which may appear adequate in some applications, but we must bear in mind that the input port of the receiver side suffer from similar effects. The use of T-coil can dramatically increase the bandwidth and improve the return loss in both transmitters and receivers. The penalty is the area consumed by the T-coil's inductor. Current mode dividers. In figure 2a, the respective figure shows the figure 2. We recognize the symmetry of this arrangement, predicting that node A and B have the same voltages and can therefore be shorted to each other. This leads to simplified topology of the figure 2c. So the figure 2b is the simplified topology of figure 2c. A series peaked circuit. We then conclude that 1 CB has no rule for the transfer function V0 1 by I in this network improves the bandwidth only as much as series peaking does. The T-coil principal role here is therefore achieved broadband matching. So here the T-coil is used for the principal role for the broadband matching. So the figure 1 is a basic current mode divider, and the figure 2 shows the simplification of that is the equivalent circuit of the current mode divider, and the figure C is the simplified of this equivalent circuit of figure B. This is the simplification of the figure B current mode circuit divider. So the voltage mode divider. Broadband transmitters can employ voltage mode output interfaces to save power. Illustrated in the figure below, the idea is to design a CMOS inverter such that it provides a Thevenin resistance RT is equals to RL. So we have to divide a CMOS inverter which provides a Thevenin resistance RT is equals to RL. When M1 or M2 is on, which can be shown that for a given output voltage swing, this approach consumes 1/4 of the power of the current mode counterpart. The width of M1 and M2 are programmable to compensate for process voltage and temperature variations. Consequently, the inverter voltage node sustains a heavy capacitance. This approach suffers from two disadvantages with respect to the current mode devices. The basic T-coil based voltage divider exhibits the transfer function. Therefore, I in the input current is equals to input voltage by RT plus RL. So, which can be written as I in equals to V in by resistance RT plus RL. We observe that if Cp is equals to 0, this circuit presents a constant resistive impedance equals to RT. To this result in indeed similar to the result we found in the relation to the circuit in the figure 1. At its first stage of glance, the output resistance may appear to be the sum of 1 by Gm by R0, which is the resistance looking into the left node, and R0, which is the resistive looking into the right node. And however, using the step-by-step procedure we follow the differential pair, one can verify that Vx is equals to 2 R0 Ix and R equivalent is equals to 2 R0. This result being exact, that is no approximation, may seems surprising. Indeed, the resistance looking into V1 alone can be approximated by 1 by Gm. However, using the step-by-step procedure we followed for differential pair, one can verify that Vx is equals to 2 R0 Ix, R equivalent is equals to 2 R0. This result being exact may seem surprising. Indeed, the resistance looking into a V1 along with the approximation of 1 by Gm. However, the resistance looking into the V2 is 2 R0. One explicit Ix on this right side and one mirrored from the left side. When added to multiplied by R0, they produce a voltage that is twice as large as equivalent. This example also illustrates however the differential current going into the current mirror does not produce a differential voltages in the two nodes. The reader can verify that the amplitude of V2 is approximately 2 gm into R0 times of V1. In summary, to determine the resistance between two nodes in the linear time inverter circuit LTI circuit, we apply a set of differential currents Ix and minus Ix to the two nodes. Measure the resulting voltage difference between the two nodes Vx and Vx by Ix. Alternatively, we can apply a voltage source Vx between the two nodes, measure the current Ix that flows from the one node to other through the voltage source, and find Vx by Ix. Thank you.